Recall our examples about ministers in a row. Canadian cabinet consists of 39 ministers. How many ways can we arrange them in a row for a picture? Because the arrangement is in a row, we can create some kind of pictorial representation of what is about to happen. And then we have to think about what are the possible options for each particular spot to be taken in the picture. There are 39 people altogether. So for the first spot, there are 39 possible people to choose from, 39 different options. For the next spot, because people are distinct and we already picked one, there's 38 people available to be chosen, and so on, all the way down to 1. Because we are picking them all in order successively, we actually are employing a multiplication principle and have to multiply all of these numbers together. Now, we've already seen this kind of from a number all the way down to 1 multiplication, and we're going to see this a lot more often in counting. So we're going to create a notation specifically for this type of thing. We define it as a factorial, which is denoted by an exclamation mark. So we take the largest number that we're starting with, 39 here, and if we are multiplying all the way down to 1, that is what we're calling a factorial. So this would be 39 factorial. Not 39, but 39 factorial. For any number r, we can define it in a similar way. Now, it doesn't matter whether you work from 1 all the way up to the number or from the number all the way down to 1, whichever way you prefer. Normally, when we arrange things, the first object has the most number of options, so we normally start by the largest number and then take away 1 from it, take away 2, and work all the way down to the bottom. However, again, if you prefer to think of it as counting all the way up to r, then that works as well. Because this comes up so often in counting, we don't just want a notation. We want to be able to refer back to what exactly does it count. And r factorial, whenever we arrange things in this way, thinking about the ministers, is always the number of ways to arrange r distinct objects. Now notice here, first of all, that the objects have to be distinct. So thinking back to when we are composing words where letters can be repeated versus people when they cannot, the factorial represents arrangement of distinct objects. The other thing that is important here is that this is the situation where order matters. It matters how people are arranged. If two people swap spots, for example, this is already a different arrangement. So for the factorial, order matters. In this chapter, we're not going to work with the factorial numerically all that often. It's actually going to show up later in one of the units closer to the end of the course. But it is nice, now that we've introduced it, to be able to somehow compute it and be able to simplify expressions with it. So just for a couple of quick examples here. First of all, let's just compute some factorials. 1 factorial is 1. 2 factorial is 2 times 1. And if you want to compute it, it's going to be 2. 3 factorial, again, working all the way down, 3 times 2 times 1. And if you multiply through, it's going to be 6. 4 factorial is 4 times 3 times 2 times 1. And what you already notice is in 4 factorial, this expression of 3 times 2 times 1 repeats itself. This is 3 factorial. Because I already know that this is 6, 4 factorial is simply 4 times 6, or altogether 24. 5 factorial is going to be 5, 4, 3, 2, 1. And again, in a similar fashion, I notice that this was just computed as 4 factorial, so I can simplify my calculations a little bit. So this is going to be 5 times 4 factorial, or 5 times 24, or altogether 120. What about something like 0 factorial? Obviously, factorial cannot be defined for negative numbers because it's a number of ways to arrange some number of objects, but we could have 0 objects. What are the number of ways to arrange no objects at all? Well, in fact, there is exactly one way to arrange nothing. There is always one way to do nothing. Simplify the following expressions. So here we have 7 factorial divided by 3 factorial. Don't just go and start canceling things out. We have to think about what the factorial represents. So 7 factorial is 7 all the way down. 6, 5, 4, 3, 2, 1. Divided by 3 factorial, which is 3, 2, 1. So of course I notice that there are common factors on top and bottom that I can cancel out. And what I'm going to be left with is 7 times 6 times 4 times 5 times 4. Things like this, it is very tempting to say, oh, well, 12 divided by 3 is 4, 4 divided by 4 is 1, so this is actually just 1. That is not at all how this works with factorials, because these are not themselves factors, right? They're factors within a larger chain of factors, so we have to work with them carefully and not forget that we cannot simply cancel things out within the exclamation point. So this is my 3 factorial times 4 factorial, so 4, 3, 2, 1, divided by 12 factorial, 12, 11, 10, 9, all the way down to 1. So you already notice that while I can, in fact, for example, 3 times 4 is 12, cancel these two things out, the rest of the simplifications are going to have to occur within the rest of the factors. So the answer isn't going to be a nice, pretty formatted thing, but if you want to simplify further, you actually can. Let's take a look at some of the sort of more structural examples. So for example, here I have n plus 2 factorial divided by n. Again, I cannot just cancel something out within the brackets. I have to think about what those brackets represent. So n plus 2 factorial means I'm going to start with n plus 2 and work my way down from n plus 2 all the way down to 1, divided by n factorial. So n minus 1, n minus 2, all the way down to 1. And here's where I notice that these two portions are actually the same. N plus 2 factorial has n factorial living within it, so that I can wholesale factor and cancel out. So what's going to remain is actually just going to be n plus 2 times n plus 1. So factorials can be simplified really nicely, especially if the numbers that you're taking factorials of are close together. Similarly, it's going to look like this in this example here. So n minus 1 factorial is n minus 1, n minus 2, all the way down to 1. Whereas n plus 1 factorial is n plus 1, you subtract 1, you get an n, and then n minus 1, n minus 2, all the way down to 1. And I can see that the entire top appears on the bottom, and the only things not factored out on the bottom, or not canceled out on the bottom, are going to be n plus 1 and n. Working with factorials gets easier with practice, so does everything in life. So the more examples you're going to do, the better. Now, again, we're going to come back to this material later in the course, but this practice at this point in time is also useful. What can I do here to simplify this? I have 8 times 7 times 6 factorial. So I have 8 times 7, and then 6 factorial, 6, 5, 4, 3, 2, 1. Well, and I notice that I have numbers from 8 all the way down to 1, so this, in fact, is 8 factorial. Make sense? I am multiplying all of these things together, and I'm also matching the type of pattern I already noticed in the previous example. N minus 1 factorial times n. So what I'm going to have here are all the numbers from 1 to n minus 1 multiplied, and then also multiplied by n. So the answer to this question is going to be n factorial. Double check to make sure you understand how I got that simplification, so that it's easier for you to actually work with factorials in the future. We will now focus in on two central concepts within counting: permutations and combinations. Permutation is an arrangement of distinct objects where the order matters. This is key. In this case, the order matters. The way that we denote permutations is P, and then we list two parameters, n and r. This will represent the number of permutations. So again, arrangements where order matters. You can think of maybe arranging objects in a line for a picture. We're going to have n objects. That's what n stands for. And R stands for how many at a time are we going to consider. So taking R at a time. So for example, when I have, let's say 39 ministers and I want to arrange 19 of them in a picture for a picture of the cabinet, the number of ways I can do it is permutations of 39 objects taken 19 at a time. A combination is a selection of distinct objects where the order does not matter. So this is going to be one key difference between permutations and combinations. The way we denote that is C for combinations and R. However, more often, we actually, because we use combinations quite a bit, we're going to use this notation. So this is actually read as N choose R. Okay, so if you see this big bracket, N on top, R on the bottom, we read it as N choose R. And this will denote the number of combinations, so arrangements where the order doesn't matter. So you can think of the team of members. When you put people onto the team with no assigned roles, the order of how you choose the members doesn't actually matter. This is going to be N objects or people. And again, it's going to be taken R at a time. So for example, if you had 39 ministers and you were picking 19 of them to be on a committee with no order at all, simply to form a committee, a set of people, you would have 39 choose 19 ways to do so. Interestingly enough, the word combination occurs in real life in slightly different way. So if you think of a combination lock that you have on like lockers in school and stuff like that, at a university, at a gym, we call it a combination lock. But it should really be called a permutation lock because the order of the numbers you're putting in for a key combination actually matters. Okay, so this is one time when the math lingo disagrees with the English use of the word. Let's just compute some permutations first. So we're going to directly try to figure out what the numbers are. So P41 means a number of permutations of 4 objects taken one at a time. So think about this. I have 4 distinct objects, and I'm going to try to arrange them in a line where order matters if I take one at a time. So I can pick this first object and arrange it in a line. There's only one way to arrange one thing in a line, but I can pick this object or this object or this one or this one. So there's 4 choices, and for each one of them, there's only one way to arrange it. Therefore, P of 41 is just 4. Next one, I have 7 objects, and I want to arrange 2 of them at a time. So 2 of them means I am going to have 2 spots, again, in a line and a picture, if you prefer a visual image of that, and I have 7 objects to choose from. The number of options for the first one is 7. Remember, the objects in both of these cases have to be distinct, so the number of options for my second object is going to be 6. I have to multiply them together in order to obtain the final answer. So this is my first choice, and this is now going to be my second choice. Pn1, the number of ways to arrange n permutations of n objects taken one at a time. So as opposed to maybe picturing the 4 objects in your head like we did last time here, I'm going to think of the number of positions in my picture that are available, which is only 1. I'm going to take them one at a time. So I'm going to pick 1 representative to stand in the picture, and I have n choices for such a person. Therefore, altogether, I have n options. Permutations, n objects taken 2 at a time. So I'm going to follow a similar logic to the one I had before, except for now I have to generalize it to n. So the number of options for my first object is going to be n, and the number of options for my second object is going to be n minus 1, because they have to be distinct and I cannot repeat them. And I'm going to multiply the 2 of them together to produce the final answer. How can I extend that logic to number of permutations of n objects taken 3 at a time? So I am using the exact same format, 3 at a time. For the first object, I have n options. For the next one, I have n minus 1. And for the next one, I have even 1 less, n minus 2. And I'm going to multiply all of them throughout. Okay? What about n objects taken n at a time. So now I have n spots for people in my picture, or however, again, you want to actually visualize this in your head. For the first spot, we have n choices, n minus 1, n minus 2, all the way down to 1, because we have n objects and we're going to actually take all of them and arrange them in order. Now this is something that we've just seen on the previous page. This is n factorial. So the number of permutations of n objects taken n at a time is just a number of ways to arrange n distinct objects, which is exactly what n factorial represents. Overall, if you have n objects and you want to take them r at a time, we can generalize this kind of thinking into a more direct formula. So I'm going to have r spots here, and I'm going to think about how to put one of the n objects into each one. For the first spot, I have all the available choices, all n of them. For the next spot, I have n minus 1, n minus 2, and so on. What is going to be the number in my last spot? I have r spots altogether, so I'm going to have to keep subtracting until I have filled in r spots. And hopefully, counting the number of elements in this set with a formula is going to come in handy here, because what I actually need here is n minus r plus 1. The number of objects minus the number of positions plus 1. Okay? We can take a look at this and try to think of how we can represent that with a factorial. So if I start with n factorial, for example, if I carry this on through until the very end, I'm going to end up with a bunch of extra terms I'm not using. So if I want to write this out somehow, it's going to be n factorial divided by something. The terms that follow this and end up in 1 will have to be cancelled out. So what goes next? Well, n minus r plus 1, the next step is going to be n minus r, and then n minus r minus 1, all the way down to 1. So this is also a factorial all in itself, with the largest term being n minus r. So the thing on the bottom here is actually n minus r factorial. If you don't believe me with this logic, I encourage you to open up the brackets for the factorial here and persuade yourself that what you get is actually this formula. Because a lot of the times, just for shorthand writing, we will write the number of permutations of n objects taken r at a time as n factorial divided by n minus r factorial. Now these are permutations. So again, remember, permutations is when the order matters. Next up are combinations. So that is the arrangements of the objects when the order does not matter. Again, remember, our notation here will represent 10, choose 1. So the number of ways to choose one object out of 10, with order not actually mattering whatsoever. So if you have 10 objects to choose from and you're picking one, how many different ways can you do that? Well, you pick either the first object or the second or third or fourth or the 10th. So there are 10 different ways to pick one object out of 10. And this 10 doesn't matter if I replace it with n. If I have n objects and I'm picking just one, there are n ways to do so. If I have 7 objects and I'm choosing 7 of them, all 7 of them, how many different ways can I do that? Well, there's only one way to pick everything, so 7 choose 7 is going to be 1. And similarly, if I have n objects and I'm going to choose all n of them, there's only one way to pick everything. Now, let's take a look at this. I have 10 objects and I'm going to choose 9 of them. So imagine I have 10 players that I have available, and I need to compose a team consisting of 9 people. How many ways can I do that? Well, the way to think about this here is if you have 10 objects, so let's say you have 10 little stars, if I'm going to pick 9 of them, hang on, there we go. If I'm going to pick 9 of them, that's equivalent to saying I am not going to pick this one. The moment I decide which one I do not pick is the moment I decide which 9 I do pick. So picking 9 players out of 10 is the exact same as picking one player that you are not gonna want. And that we've already calculated. There is exactly 10 ways to choose one person out of 10 that you do not want to be on the team. Okay, so this is a very important connection. Picking 9 objects out of 10 that you want is equivalent to picking one object out of 10 that you do not want. And similar logic will apply here. If I have n available options and I need to pick n minus 1 of them, choosing n minus 1 I want is equivalent to choosing the one I don't want. So therefore, there are n possibilities for the object that I do not want. So n, choose n minus 1, is going to equal to n. The number of permutations of distinct objects that we've already discussed can also be calculated through the combinations. So connecting permutations and combinations. Remember that the thing to keep in mind here is that permutations have an order and combinations do not. So how are we going to approach that? Let's think about this. In order for me to form a permutation, first of all, I can choose which objects I actually want. So out of the n objects available, I'm going to choose r of them. Okay? This is choose r objects you want. But now, combinations are teams. So the order doesn't matter. So far, there's no order. I have chosen r objects I want, but I haven't ordered them yet. Now I have r objects. How many ways are there to arrange them in a row? I have r objects. The number of ways to arrange them in a row is simply r factorial. So this represents arrangement of those r objects. Okay, I think this is actually quite profound. So the number of permutations, the number of ways to arrange r objects out of n is to first choose the r objects you want and then arrange them in order. Once you have that, this will also allow us to find a formula for the number of combinations. So what I have is n choose r times r factorial is equal to the number of permutations, which I already know to be equal to this point right here. So let's just rewrite this formula. So what I have is n choose r times r factorial equal to the number of permutations, which I know to be this number, n factorial divided by n minus r factorial. If I would like to figure out what is my number of combinations, I simply have to solve this big equation for this number, which actually just boils down to dividing both sides by r factorial, and then remembering that when you're dividing, it's the same as multiplying by the reciprocal, so this r factorial can actually join the denominator here. So altogether, solving that for n choose r will give us n factorial divided by r factorial n minus r factorial. Okay? It looks like a big ugly formula, but remember, you do not actually have to memorize it. And in fact, if you want to compute it, things like Wolfram Alpha, which is a computer system available on the internet, it's like a big calculator, will simply actually calculate the choose function for you directly. Now, let's put this theory to practice and do several exercises about calculating with permutations and combinations to see how this works. Right, let's dive right in. Suppose we toss a coin 8 times and record the results. How many different records are possible? How many records contain exactly 2 tails? How many records contain at most 2 tails? We're going to put everything that we've learned so far in the counting unit to use. So, starting off with the first part, how many different records are possible? We toss the coin 8 times. So I have 8 options back to back to back. In the first toss, what are my possibilities? I either get heads or tails, which means that I have 2 options for my first toss. What about the second toss? It's independent of the first one. The coin is assumed to be fair, unless it says that otherwise. So I have 2 options for the second toss as well, heads and tails, and so on and so forth, all the way through 8 tosses, and they happen consecutively. So I have 2 times 2 times 2 times 2, 8 times altogether, for 2 to the 8 available different records. What about how many of these records contain exactly 2 tails? So once again, let's think about my actual records. So I am tossing the coin and I'm recording what happens, right? So for example, heads, tails, heads, tails, heads, 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 heads. This particular record has exactly 2 tails in spots 2 and 4. But of course, tails can happen in any of the other spots. Now, though, once I have determined where tails are, so for example, I don't know, here and here, the rest of the record is determined. I'm only allowed, or I'm only interested in 2 tails. So once I have placed my 2 tails, everything else has to be heads. So all I have to do is, among the 8 possible positions, choose the 2 where tails will occur, and that will determine the rest of the record. Choosing means using combinations. Out of 8 available positions, 1, 2, 3, 4, 5, 6, 7, 8, for the 8 tosses, I'm going to choose 2 where tails will appear, and then by default, everything else will have to be heads. Alternatively, and this will be equivalent, out of the 8 positions, I can choose 6 where heads will occur. So I can choose the 6 spots for the heads, and that will determine where the 2 positions for the tails are. And in fact, these 2 numbers are actually going to be equal to each other. And if you want to calculate using the formula from the previous page, it's going to be 28. The next up is how many records contain at most 2 tails. So what does this at most actually refer to? At most means I can have 2 or fewer. So I can have 0 tails, I can have 1 tails, or I can have 2 tails. And I'm going to actually calculate each one of them separately. So let's go right ahead with 0, 1, and 2 tails. How many ways can I toss the coin 8 times and record 0 tails? So I want to see no tails at all. What are the possible options? Well, if there are no tails, that means that every single thing in my record is heads, and there is only one way to do so, is to toss all the heads all the time. If I am to see exactly 1 tail, that means that out of the 8 positions, there has to be exactly 1 spot where tails occurs and everything else is heads. So out of the 8 positions, I'm going to choose 1 position where that tail is going to appear and everything else will be heads. If you calculate this, this will actually going to be 8, which also makes sense because tails, the 1 tails that I'm going to see can happen in the first spot or second or third, fourth, fifth, sixth, seventh, and 8th. 8 possible options. The 2 tails, I've already calculated it here. So my possible choices for 2 tails are 8 choose 2 or 28. Now, I am interested in the number of records containing in most 2 tails. So no tails or 1 or 2. And these can happen only 1 at a time and not simultaneously, which means that altogether I am going to add all of them up. There is one way to see no tails at all, plus, by addition principle, there's 8 ways to see 1 tail, plus there's 28 ways to see 2 tails. And that is going to be my total number possible. Now, I strongly recommend generally, I know that everybody is more comfortable with actual numbers, but I strongly recommend actually leaving it in a simplified form. Because if you have these numbers and you give me the final answer as whatever number this comes out to be, I do not see your logic behind computations. However, if you give me your final answer as 1 plus 8 choose 1 plus 8 choose 2, I can see what logic went into these calculations. There's one way to toss all heads, there is 8 choose 1 ways to see 1 tails, and there is 8 choose 2 ways to see 2 tails. So this tells me what your reasoning is, this one does not. So if you make a small arithmetic mistake here, I won't be able to catch it. Whereas if you do it here, I'll at least be able to follow your logic through. Next up, we have a law firm that has 12 senior partners and 20 junior partners. They wish to make a committee of 6 people, and we're interested in actually 2 different things. First, how many different committees are possible overall? So no restrictions on who goes into the committee. So I have 12 plus 20, I have 32 people in total, and my committee is to contain 6 people. Now, a committee is just a set of people, it's a team. No order is necessary. So out of the 32 people, I'm going to choose 6 to be on my committee. 32, choose 6. Whatever number that ends up being. Again, I'm not so much interested in the number itself. I'm interested in the logic that led me to derive that number. So this is a much better answer than the actual numerical version. How many different committees are possible if there must be exactly 4 senior partners on it? Okay, so I'm going to start by choosing 4 senior partners out of the 12 I have available. 12, choose 4. So this will correspond to senior partners. Now, I'm not done yet because my committee has to have 6 people. And I'm told I have to have exactly 4 senior partners, so I can't have 5 or 6, which means that once I've chosen my 4 senior partners, the 2 other people on the committee must come from junior partners. So 2 other people have to be chosen from this 20. So 20, choose 2, will give me the number of junior partners that I have to supplement my committee with. And because both of these things have to happen in order to form a committee of 6 people, I'm going to multiply them by each other. 4 people go out for brunch. How lovely. They go to a restaurant that has 8 different items available on the menu. Okay, brunch place, 8 different items. Pretty reasonable. How many different orders are possible, assuming each person orders 1 item? Okay, so each person, so I'm going to have 4 people, 4 people going out to brunch, and there are 8 different items. The first person has all the possible options. So they have 8 options for their brunch item. What about the next person? How many options do they have? This doesn't say that they have to order different things. It's just saying how many different orders. So the next person isn't restricted by what the first person chose, so they too can choose 8 different items. Out of the 8 different items, they have 8 different options, and so on and so forth. Because all 4 people actually have to order a brunch, I will have 8 multiplied by itself 4 times. What about part B? How many different orders are possible if everyone must order a different item? This we already know is going to be a slightly different setup. I have 4 people. The first person has 8 choices, but the next person doesn't have 8 choices. They cannot pick what the first person chose, so there are 7 options for the next person down. There are 6 options for the next, and finally 5 options for the last person. So I'm going to have multiplications throughout, 8 times 7 times 6 times 5. This is actually the same as the number of permutations of 8 objects taken 4 at a time. The other way to calculate this will be, look, there are 4 people and 8 items. They all must order different things. So I can choose the 4 items that they will order, so they will get 4 items to the table. Now, everybody, though, it doesn't say that they're going to share. It means that everybody has to get their own personal brunch item. So I'm going to have to multiply by the number of ways that the server will have to place the items in front of the people. They chose 4 items to purchase. There are 4 factorial ways to actually place them on the table or order them around the table. I'm going to say place them on the table. Okay? And all of these ways are all different possible ways of counting the exact same thing. The nice and the hard thing about counting is there's often more than one way. So practice more so you can find yourself the ways that you are comfortable with. Suppose you have to construct a truth table for 3 Boolean variables, something we did at the beginning of the course. So my variables are P, Q, and R. How many rows would you need? What about 4 variables? Remember that Boolean variables have true and false values. So there's 2 options for each of the variables. If I start off with 3 variables, P, Q, and R, I'm going to calculate the rows by thinking about what my possible options are. For P, I have 2 options. It can be true or false, so 2 options here. For Q, there's 2 options here as well, true or false, and for R, there's also 2 options. So altogether, I have 2 cubed or 8. And we can reaffirm that in the beginning of the course, when we're constructing tables for 3 Boolean variables, we needed 8 rows altogether. But now, we don't need to wonder why that's 8 and whether, in fact, we've covered all the possible choices. We know for a fact that it's going to be 8. So once you've hit 8 rows, as long as they're distinct, you know you've covered all of your possibilities. What if you have 4 variables? So if I have 4 variables, 1, 2, 3, 4, the logic is going to be the same. I have 2 possibilities for my first variable, true or false, 2 for the next, 2 for the next, and 2 for the last one, 2 to the 4th. Which means that for n Boolean variables, I'm going to have 2 to the n rows. Boolean variable tables grow very quickly. Let's think about choosing pin numbers and what are the different ways to do so and why or why not some things are more secure than others. How many different pin numbers are there? Now, every system you use has different format for the pin numbers to be chosen. So in our case, we are looking at 6-symbol pin number, and you decided you want it to be 3 numbers followed by 3 letters. So I have 3 spots, each has to be filled in by a number, followed by 3 more spots, each has to be filled in by a letter. What are my options here? For the first number, I have 10 different options, 0 through 9. For the next number, I am not given any restrictions on whether or not they have to be distinct, so I still have 10 possibilities. Next one is also a number, so 10 more. And then I'm told that what's to follow are going to be 3 letters. Again, nothing to say whether or not they have to be distinct, so I have 26 choices for the first letter, 26 choices for the second letter, and 26 choices for the last letter. Multiplying throughout, I can see that my final answer is going to be 10 cubed times 26 cubed. You calculate that, you see how many different pins are available. Next up, how many different pin numbers have no repeated numbers and no repeated letters? So we're going to have to take our logic from above and somehow modify it lightly. What do we have? For the first number, I have 10 choices. But the next number cannot be what the first one is, so I'm going to have only 9 choices. And the third number, I'm going to have 8 choices. For the first letter, I have 26 choices. For the second, 25. For the third, 24. Multiplying them all together will give me the final answer. How many different pin numbers have distinct letters that appear in alphabetical order? So let's think about how we're about to calculate that. So first of all, again, I'm going to think about placing all the things that I need. First of all, I'm actually going to start with the 3 numbers. Doesn't say anything about the numbers, so my number choices are going to be completely general. I have 10 choices for the first number, 10 choices for the second, and 10 choices for the third. But now what am I going to do? I need to have distinct letters, and they need to appear in alphabetical order. Okay, so first of all, I'm going to have to choose the 3 letters that go into these 3 spots. The number of ways to choose 3 letters is 26 choose 3 for all 3 of them. Once I have chosen my letters, let's say the letters I chose were K, G, and A. How many ways can we arrange 3 letters in alphabetical order? Well, if the order is alphabetical, there's only one way to do so for any set of 3 letters. So in this case, the order is going to be A, K, G. But there's exactly one way to do so in alphabetical order. So this is going to be followed by multiplying by 1 to signify just that. To recap, we have 10 options for each of the numbers, followed by choosing 3 letters and having only one possible way to arrange them in alphabetical order. So overall, for the number of these different pins, we're going to have 10 cubed times 26, choose 3. What is the probability of someone guessing your pin? Well, how many different pins are there? We've already calculated that. How many of them are going to be a desirable outcome? How many pins do you, as a person like that, use for a specific person? 1. So, remembering our formula for the number of desirable outcomes divided by the number of total outcomes, there is only one pin that you would want to guess, and there is altogether 10 cubed times 26 cubed options that are available to a hacker. How many different pin numbers have 2 appearing in them? So the number 2. Let's think back to the format here. So the letters don't really matter because obviously number 2 cannot appear amongst the letters. So I'm interested in seeing a 2 appearing in one of the spots here. So where can it go? It can go here, or it can go here, or it can go here. Now the problem, of course, is it can be in one spot, or it can be in 2 spots, or it can be in 3 spots. So having a 2 appear means at least one 2 appears, but it could be more. Here is where thinking about the complement really helps. The number of ways to have a 2 appear is all the possible pins taken away the number of pins where no 2 appears. So I'm going to take the total and subtract the things that I do not wish, which are no 2 appearing. Okay, can we agree that this is the exact opposite of having a 2 appear? I hope so. The number of total pins that we've already discussed is 10 cubed times 26 cubed. Now, how many different pins have no 2 appearing in them? The reason this is easier to calculate is because now I know exactly what kind of thing can go into each spot. So let me reproduce my spots again. If I'm not allowed to have 2 as a number, instead of 10 options for a digit, I only have 9 options for a digit here, 9 options for a digit here, and 9 options for a digit here, followed by all the possible options for the letters. So altogether, I'm going to have 10 cubed times 26 cubed minus 9 cubed times 26 cubed for these different number of pins. Notice that all of the counting questions can actually be turned into probability questions, and the way to solve them then would simply divide by the number of total pins that we calculated in part A. So from now on, if you see a question that involves counting and probability, the probability part will be done simply by applying the already well-known principle of dividing the number of desirable outcomes by the number of total. Next up, let's think about the strength of the passwords. A lot of times you go to a new service, they ask you to create a strong password, and they list a bunch of prerequisites for what makes a password strong. At least 12 characters, a mixture of upper and lower case, a mixture of letters and numbers, and having at least one special character included. What I am interested in is if you stick to the minimal requirements and have exactly 12 character password that follows these rules, is it better or worse than a password double the size that is composed of only lowercase letters? So is the claim that something like this produces a strong password actually legitimate? So I have 12 characters, so I have 12 spots where things can go. 1, 2, 3, and so on, all 12 of them. What are my choices for each spot? Now, of course, some humans follow patterns. So a lot of times, People will, for example, start with an uppercase letter and then followed by a lowercase letter and then have a number and then have a special character and then repeat it or something like that. We're going to not complicate things too much and not think about these types of idiosyncrasies. We're literally just going to list all the possibilities for every spot. So I'm allowed to use upper and lowercase letters. So for the lowercase letters, I have 26 options. For uppercase letters, I have also 26 options, same letters, but our uppercase. Now, I also am allowed to use numbers. There are 10 of those. And I am also asked to use special characters, or at least one special character. Now, if you look at your keyboard and try to count special characters, you might come up with different number than I have, but I've counted approximately 30 different special characters. Between an exclamation point, an asterisk, the greater or less than sign, comma, and period, and so on, let's say approximately 30. So, for each spot, I have 26 plus 26 plus 10 plus 30. So in total, I have approximately 92 different options. So for each spot, I have a choice of 92 different characters, which means that altogether, I have 92 to the power of 12. What about a password that has 24 characters, but all of them are lowercase letters? So 24 spots, and all of them are lowercase letters. So I have options that are just lowercase letters, 26, 26, 26, and so on. So here, altogether, I have 26 to power 12. How different are these two numbers? I mean, first of all, I can obviously see that this one is going to be bigger. So this does create a better password. Oh, sorry. So altogether, I have 26 times 26 times 26, 24 times. So 26 to the power of 24. And now, the task is to compare these two numbers. Which one is bigger, 92 to power 12 or 26 to power 24? Now my regular calculator cannot handle numbers that are that big, so I'm going to go ahead and look for Wolfram Alpha, which is essentially a big online calculator. The nice thing about Wolfram Alpha, well, there's lots of nice things about Wolfram Alpha, but in particular, it actually interprets language. So I can simply say, which one is bigger? And my options here are 92 to power 12 or, 26 to power 24. You press enter and wait for the results. Scrolling down to the screen, we see that my input was the maximum between 92 to power 12 and 26 to power 24, with result of 26 to power 24 being a bigger number. We can double check this by saying, okay, well, maybe we don't believe that. So that means that the longer password with only lowercase characters is actually stronger. Is that true? So why don't we subtract the second from the first? If the result is a positive number, that will mean that the first number is bigger. If the result is a negative number, it means the second number is bigger. And here we have yet another confirmation. 92 to power 12 minus 26 to power 24 produces a negative result, which means that we subtracted a bigger number than we were subtracting from. So, back to our example here, that means that this number is bigger than this one. So having a 24-character password that is composed of only lowercase letters is better than having a so-called strong password that only has 12 characters but has a mixture of all of these possibilities. This is why in cybersecurity world, the password phrases are now more popular. You create a longer password phrase, so you link simple words together. But if it's longer, it's better than a shorter password with more characters choices. Okay? Password phrases for the win.